Hello, good morning, good afternoon, and good evening once again. I took some of my time to share another video with you. This time, I want to talk to you about how calibrated resistances are measured, how current is measured, also known as shunts, which we constantly have in mind in cathodic protection. It's used to interconnect sacrificial anodes to the pipe, and usually an anode is disconnected in series, but it's a shunt, a calibrated resistance in series. They are also used to interconnect pipes that are in parallel or at perpendicular crossings, also known as bonds, and their purpose is to direct current, return current, bring back interference currents, or activate galvanic systems. I want to emphasize this point about how to measure current in shunts and calibrated resistances, because we need to pay special attention to the sign that the reading gives us at that moment. I'm going to explain how to connect it, where to connect the positive cable, the red cable of the multimeter, and where to connect the black cable or the negative cable of the multimeter. Multimeter, multitester, multi-command. They go by several names, but these are the measurement tools we use to measure voltages. And sometimes I'm explaining, measuring potentials in pipes and identifying if it's a pipe or an anode. In the field, cables with identical colors aren't labeled. We must identify them first to measure and analyze. As you know, my methodology is much more practical than theoretical, meaning I focus on practical exercises. I set up a mini lab to explain better. We need to identify them beforehand so that we can then take measurements and do the respective analyses. As you always know, my methodology is much more practical than theoretical. That is, I try to support it more with practical exercises. I made a mini improvised laboratory for you, so it is a way of trying to make myself understood much better. Without further ado, let's continue. Before we dive in, don't forget to subscribe to my channel and turn on notifications to stay updated with my content. For this occasion, I prepared this laboratory where you can see this steel sheet, which will serve as a beam that we are going to try to protect cathodically. Here we have an anode, an aluminum soda can, which I'm going to use for this exercise. And this is a test station that I'm including. We find these TJ stations a lot in the field in a PVC pipe, at waist height a little higher. And the TJ stations have connection points for cables. In this case we have two cables. I don't know which one is the anode and which one is the cathode. I'll show you how to check this and how to identify them. But these big finks are very common to find in the field. There are other types and models. The purpose is to have terminals where the cables can connect and have securing screws. I repeat, this is one model. There are other models, some that are post type with a little hat, a progressive identifier, or kilometers. Basically, I built this mini laboratory for you, and here we have a reference cell to measure the potentials. I'm going to keep it fixed in one position, because I'm going to measure potentials with fixed cells. So, sometimes, many buried pipes have two wires soldered to them that come here to these big fins. These could be the two wires but they are two wires that are soldered to the same structure, and we identify that through measurements. But if there's one wire soldered to the pipe and another wire soldered to an anode, we also need to have the ability to identify that. In this case, to interconnect this structure with the anode, we use the famous calibrated resistors. This is a calibrated resistor. Let me bring it closer to see if you can see it. It's 0.1 ohm. Let me fix it right here. And now to see if we can actually see it. Let's see if I can do it. Is it hard to see the reading when looking at it in person, right? Here it is. It's from the brand Cathodic. It's 0.1 ohm because you can see the omega symbol. And it says that 1 ampere is equal to 1 millivolt to 1 volt. The capacity of the Chun-Socios is 2 amperes. If you see, all the calibrated resistors of this type come with their specifications and capacities. What is the calibrated resistor? This wire here, this wire is the calibrated resistor. Where do we measure this resistance? In these two little pieces. We always place them in these two little pieces, not here, where the fastening screws go. It's here, in the two little pieces that we measure on the millivolt scale. There are two ways to measure currents in cathodic protection systems. One is using a calibrated resistor, which is the most common way to measure both alternating and direct currents. With these devices, alternating and direct currents are measured. Here we have this clack mirror instrument or clamp meter that is used in cathodic protection to measure current. However, these devices, when the current is less than 0.100 milliamperes, will not register it, will not sense it. They don't measure that current below 100,000 amperes because their sensitivity starts from 0.1 and up. So starting from 0.1 is when this device measures current. We simply place the cable here and set it to alternating amperes. There you see the sinusoidal shape, or direct amperes, which is the line with the cemented dots. That means it's 600. This means it's 600, and this means it's alternating, because it has the sinusoidal wave. It also has the capacity to measure alternating voltages and direct voltages. It measures the omega sign, which indicates that it's for measuring resistance. It measures continuity. This symbol is for sound. Alternating current and direct currents. It also measures capacitance, because this is the symbol for capacitance. It measures frequencies in hertz and also measures in millivolts. So it's a piece of equipment that's practical in the field. But when it's below 100 milliamperes, we have to use calibrated resistors. This is one. We would have this other model of calibrated resistor. Notice that it also has its, let's see if we can see it. It says 5 amperes, 50 millivolts. And at the points where it's measured is at these two screws, this screw and this other screw. This is where we put the probes of the multimeter. I have to remember that these videos are mainly aimed at beginners. There are learners who have never handled a multimeter, and I would like to explain a multi-tester, because they are multi-testers since they measure voltage up to 600 volts. We have two types of voltage: alternating current voltage and direct current voltage. The alternating current voltage is what the electric companies provide us, which is what comes into our homes, and we can measure that alternating voltage here. Notice that it has the sinusoidal symbol, which indicates that it is alternating voltage. If I set it there, it would measure external voltage. And here it would also show, I don't know if you can see it, it says
millivolts AC, millivolts of alternating current. It's not measuring anything because I'm not taking any readings. If I set it here, we can measure direct current voltages, and here we can see DC. It indicates that it measures millivolts. If I set it here, it shows millivolts, and here it says 600 millivolts. I can also see that it has the temperature symbol, which looks like a small yellow thermometer. This is for measuring temperatures. To activate it, since it's yellow, I have to press this yellow button. I press the yellow button and notice that it changes to degrees Celsius. We can also set it to measure degrees Fahrenheit. Here we can measure continuity, resistance, and capacitance. If I set it here, it's currently in mega ohms to measure capacitance. But if I want to switch to audible mode, so it beeps for continuity, I need to press this little icon here, which is identical to the one here, to activate the sound mode. When we test the continuity of a cable, if the cable is in good condition, it will beep. If it doesn't beep, it's because the cable is broken. This symbol here is for a diode, the electrical or electronic symbol for a diode, specifically for checking and measuring diodes. We can also measure milliamperes. Notice that it has the sinusoidal shape for milliamperes and amperes, but we can also see the segmented yellow lines, indicating that it also measures currents up to 600 volts. Right now, I can see it says use in BDC. Sorry, I set it to 1000 amperes, and it shows alternating current, amperes. But if I press the yellow button, since the segmented line is yellow, it switches to ADC, which is 600 amperes. If I want to measure in microamperes, because the current is much smaller, it says AC, amperes, and if I want to set it to 600, I press the yellow button, and I can see it says ADC. So basically, this is how the multimeter works with all its functions. Notice that this terminal is red. If I connect the red cable here, I can measure voltage, resistance, diodes, in this position, even temperature. The common data wire is the black one, and it also has its terminal in black, so that we don't get confused with the colors. So here we have the black color, and we know that the black cable over there should be connected here, and the red one, if I want to measure voltage, I should place it here. If I want to measure currents, I need to put it in this red terminal for milliamperes or microamperes, and if it's in amperage ranges, I should connect it here. Notice something particular when we are measuring voltage. To measure voltage, I place the black wire in the black terminal and the red wire in the red terminal where it says B. So, in this setup, it's for measuring voltages. I can turn on the multimeter, and it shows that to measure millivolts in AC, I can set it to 600. Sorry, I mean volts 600. If I want to measure currents, and it is in the ampere range, I must place it here. Listen to that alarm, that beep that's warning me. Be careful. Danger, you're at risk. Because if I measure voltage with this terminal placed here, I'm going to cause a short circuit wherever I'm trying to measure voltage. Why? Because in this setup, we're using the calibrated resistance or the internal shunt that the multimeter has. Because in this setup, we're using the calibrated resistance or internal shunt that the multimeter has. The way this multimeter measures currents is through a calibrated resistance or shunt that's inside the multimeter, exactly like this one, but it's on the inside. This means that if I currently have it connected here in amperes, and I'm going to measure voltage under that condition, I'm going to cause a short circuit. If I set this to amperes, the alarm stops sounding because I have it in the right position, because I have it configured to measure current. If I am going to measure current, I must place it either here or here. So that's why that alarm gets activated. If I just did a current measurement, finished, and now they tell me, Pedro, measure the voltage, and I don't realize I didn't make the change here, but I switched to voltage, the alarm automatically goes off, and that should tell me, Pedro, pay attention. Something's happening, there's danger. And when I see, oh, I forgot to change it and put it back here, it stops beeping. This equipment, this state-of-the-art equipment, has that capability. You don't have to be afraid of current, you just have to respect it. And when I see, oh, I forgot to change it and put it back here, it stops beeping. This equipment, this state-of-the-art equipment, has that capability. You don't have to be afraid of current, you just have to respect it. If we follow the appropriate safety measures, we wouldn't have any problems. Now then, folks, what do they tell us? What do they teach us in electronics or electricity schools? When taking measurements with these devices, measuring this battery marked red here, you can see the positive sign. It's identified in red as positive and black as negative. Using measuring equipment, the positive lead goes with positive and negative with negative. It's a universal rule. Red with red, black with black. Connecting correctly shows a positive value, 13.8 volts. Reversing wires gives a negative value, indicating incorrect connection. It shows 13.9, but negative, there's the negative sign. Using a multimeter, connect positive with positive and negative with negative. This ensures a positive reading. Correct connection shows positive. No positive sign appears. Reversing wires shows negative, indicating incorrect connection. Not following the rule for battery. That's how to measure. This is taught in school for readings. When we connect it, the value will show as positive. If you can see here, I'll turn on the light, and there it is. 13.8 volts. I don't see a positive sign because when it's positive, it doesn't show a sign. But if I were to reverse the wires, it would give me a negative value, which means it's connected incorrectly. It shows 13.9, but negative. There's the negative sign. So here, I'm not following the connection rule, at least, for measuring a battery. The rule tells me that when measuring a device, a power source, the black goes with black, negative goes with negative, and positive goes with positive, red with red. That's how to take the measurement. And of course, here we see the reading. Okay, so let me zoom in a bit more for detail. So basically, folks, this is what they teach us in school about how to use this equipment to capture readings. Okay, now let's remember that this is our big finish. My mini lab becomes an underground structure. We don't know what's beneath.